is hot in antennas and propagation? Today I'll present to you the highlight of our paper, Scaling Angle Extension of a Millimeter Wave Antenna Array Using Electromagnetic Bandgap Ground. This is a collaborative work of Xidian and Xianjiu University. I'm Professor Zhao from Xidian University, and the corresponding author is Professor Chen from Xianjiu University. This presentation will be composed of 5 parts. First, let's talk about the motivation of this work. As we all know, 5G is gradually migrating to millimeter wave bands to deliver data with higher throughput. At the same time, due to the propagation characteristic in millimeter wave bands, path loss has to be dealt with. Therefore, phased array is widely used for millimeter wave communication systems. We can see thousands of antenna elements at the base station side and tens of antennas at the mobile terminal side, creating high-gain, precise, yet narrow beams. Therefore, wide coverage capability is needed not only for communication but also for sensing applications. To create a uniform linear array with wide scaling angle, the following 3 key factors must be satisfied. Firstly, the element spacing has to be reduced to around 0.5 lambda to increase the effect of array factor at the large scaling angle. Secondly, according to array pattern multiplication, the element pattern has to be broad. Finally, the mutual coupling between the closely spaced elements have to be dealt with simultaneously. To satisfy the above 3 requirements seems to be very challenging, thanks to the bandgap and in-phase reflection characteristic of the EBG structure. If we place well-matched antenna elements above the EBG ground and form an array, the 3 requirements can be satisfied at the same time in the same band. In our design, E-shaped patches are selected for better impedance matching. Mushroom type of EBG structures have perfect bandgap property from 24 to 28 GHz. At the same time, the in-phase reflection condition is also valid in the same frequency band, as can be seen from the figure here. To clearly review the coupling mechanism between 2 E-shaped elements, we also developed a circuit model, which matches the physical model in both the magnitude and the phase responses. It is clear that the isolation between every 2 elements is more than 17 dB. The array is fabricated using multi-layer PCB technology. The layer stack is shown here. The SMPM connectors are using as the feeding ports. The scattering parameters are measured with a millimeter wave VNA, while the scanning performance of the array is evaluated in the spherical near-field chamber with a programmable beamformer. The measured scattering parameter shows that the array with the EBG ground outperform the array with the PEC ground in both the bandwidth and the inter-element couplings. More importantly, the scaling angle can improve from 55 degrees to more than 77 degrees with less than 3 dB scaling loss, which is confirmed by the coverage efficiency comparison. That's all for the highlight of this paper. Thank you for watching.